Good afternoon and welcome to Konica Minolta Sensing webinar on the CMM6 Multi-Angle Spectrophotometer. Our presenter today is Stephen Dorff, Technical Support Applications Engineer at Konica Minolta Sensing. Stephen has a background in mechanical engineering and physics. Before joining Konica Minolta Sensing, he was a research and teaching assistant. In recent years, he has been engaged in industrial image engineering and has broad experience in spectrophotometers, paint formulation, and recipe prediction. Among other topics, Stephen will discuss the multi-angle spectrophotometer's role in solving issues that arise when measuring color in modern automotive coatings. With the sophistication of new pearlescent and metallic automotive paints and coatings, it has become difficult to quantify color accurately and consistently, especially on curved surfaces. We will have a question and answer session right after Stephen's presentation. If you'd like to ask a question anytime during the presentation, please enter it in the chat box and we will answer them at the end of the presentation. Stephen, please take it away.
Thank you for the introduction. Today I will introduce the Konica Minolta CMM6 Multi-Angle Spectrophotometer. My goal is to introduce the CMM6. I'll start by introducing a few possible applications that could benefit from the CMM6. Then I will introduce some basic information on effect pigments to help you understand how they differ from more commonly used colorants. To help you understand how the CMM6 can be utilized, I will discuss the CMM6 measurement geometry, which includes an introduction to the flop index and also an overview of Konica Minolta's patented dual path technology for measuring curved surfaces. Additionally, I will highlight some of the design choices that make the instrument easy and comfortable to use, and I'll wrap up with an example of the instrument in use and address your questions. Multi-angle spectrophotometers are primarily used for measuring products that utilize metallic pearlescent interference and diffraction effect pigments, but they certainly can be useful for measuring other gonioapparent materials, that is, materials where the color changes with illumination and/or viewing angle. The automotive industry heavily uses effect pigments for both automotive finish and refinish applications, but also for interior parts and rims. Other industries also use effect pigments. These can include coatings for consumer electronics and the accessories that they use, like phone cases. Building materials like metallic finish on siding and roofing materials can also use effect pigments. Other examples include consumer goods such as toys like this fidget spinner, clothing, shoes, and of course cosmetics such as eyeshadow, lipsticks, and nail polish. Colorants can be classified into two main categories: absorption colorants and effect pigments. You are probably most familiar with absorption colorants. Absorption colorants include dyes and absorption pigments. Dyes have smaller particle sizes than other colorants and interact with light almost exclusively through absorption. They are also small enough that scattering is negligible. Absorption pigments have larger particle sizes than dyes and interact with light primarily through absorption and scattering. Both dyes and absorption pigments produce colors that have little angle dependency. That is, the color appears the same regardless of the illumination and viewing angles. I have a video showing a drawdown of an absorption pigment that's being rotated through different viewing angles. Notice how the color appears consistent with the viewing angle. Effect pigments interact with light in more complex ways. Metallic pigments add the appearance of metallic gloss. In the automotive industry, they are used to accentuate the contours of the car body. Metallic particles are larger particles that are usually flat. As the name suggests, they are composed of metal or metal alloys. These particles primarily reflect light on the surface of the flake and scatter light on the edges. As with other effect pigments, the light interaction characteristics depend on the morphology of the particles, that is, the roughness and geometry of the substrate, the particle size, the particle distribution, the particle thickness, and the pigment orientation in the medium used for application. Next, I will show you a video of a drawdown of a metallic pigment rotated in the same way as the previous video. Note how the lightness of the sample dramatically changes when the samples are rotated. Pearlescent and interference pigments both primarily interact with light through interference. To produce interference, the particles are composed of multiple layers that have different indices of refraction. The large difference in index of refraction results in large surface reflection at the boundary between layers. The light reflected from the secondary boundary layer then interferes with the light reflected from the first boundary layer. Depending on the index of refraction, the layer thickness, and the incident angle, the path length that light must travel through the layer will change. The path length will determine the wavelength dependent interference, where constructive interference results in the interference or resonant color. Color impression from these effect pigments comes primarily from two parts, as described, the interference, and two, the background material. The background can absorb or scatter. Backgrounds with large amounts of absorption have nearly a black background and result in the interference color dominating the color perception. A heavily scattering background, such as white, will have a much larger influence on the total color perception than a black background. Backgrounds with both absorption and scattering will influence the color perception somewhere between white and black. The next video clip shows rotation of an interference pigment through different viewing angles. Notice the hue and chroma shift with angle. Also notice how the interference color is more perceptible with the black background. Diffraction pigments are the least commonly used effect pigments at this time. As their name suggests, they primarily interact with light through diffraction. These pigments disperse light like a diffraction grating, similar to light dispersion through a prism. These particles are engineered with a highly reflective, usually metallic or even ferromagnetic substrate. Then they are vapor coated symmetrically with nanoparticles to create structures of parallel lines or grooves, like the lines on a diffraction grating. These particles can disperse reflected light, resulting in the color perception being very angular dependent. As you can imagine, these particles are complicated to manufacture and also expensive, and they also are difficult to apply. Automobiles and cosmetics are not the only place where you can observe gonio appearance, that is, appearance that changes with illumination and or viewing angle. Examples in nature include many birds, such as hummingbirds, insects, mollusk shells, such as abalone and mother of pearl, and the fruit of the pollia condensate berries. The natural microscopic structure of these organisms' feathers, exoskeletons, and shells interact with light and produce these effects. You can also see light interference with soap bubbles and oil films. Effects are even used in currency as a means to prevent counterfeiting bills. Notice the color shift on the US $10 and $20 bills. When color is measured, typically a spectrophotometer is used. This instrument measures the spectral transmission or reflectance of a specimen. Then the color perception can be calculated, for example in CIE L star A star B star, for one illumination and one viewing geometry. This is typically diffuse illumination with a detection angle of 8 degrees from the normal of the specimen, but other geometries exist. For example, 45-degree illumination, either annular or circumferential, with a 0-degree detection angle. These instruments work great for measuring materials that are not gonio apparent. However, Effect pigments cannot be characterized with this simpler geometry. For this reason, goniospectrophotometers are used. Gonio it simply means angle in ancient Greek, and a goniospectrophotometer is a spectrophotometer where multiple illumination and or viewing angles are used during measurement. They allow for rotations of the detector around the sample, rotations of the light source around the sample, or rotations of the sample about its own origin. And these can also be combined. These instruments are used primarily in research for measurement of BRDF, that is, bidirectional reflection distribution function. These measurements are usually large and have complex moving parts and have a cost that reflects their complexity. A multi-angle spectrophotometer is a simplified goniospectrophotometer. Multiple illumination and or viewing angles are used, but they are fixed. This reduces the size and complexity and the amount of data that has to be processed compared to the laboratory goniospectrophotometers. The portability and repeatability make the multi-angle instruments great for quality control applications and for research and development when the full BRDF is not required. The CMM6 has 1 illumination angle and 6 detection angles. Different nomenclature is used to describe these angles, so I will briefly cover the 2 most common. Conventional aspecular angles will reference the specular angle as a 0 reference. The specular angle is equal to the incident angle, but opposite the surface normal. If you're unfamiliar with the surface normal is, that is just the line that's perpendicular to the face of the sample. Here, the aspecular angle are labeled in blue, and for the CMM6 include -15, 15, 25, 45, 75, and 110 degrees. ASTM also defines observation angles. These angles reference the normal of the sample as a 0 rather than the specular, and they are shown in green. The angles on the reflective side are therefore negative, and on the illumination side are positive. For the CMM6, the ASTM observation angles are -60, -30, 20, 0, 30, and 65 degrees. When working with multi-angle instruments, using a standardized notation is helpful when communicating this information. The ASTM terminology reads as the illumination angle, followed by the observation angle, or alternatively the aspecular angle, and that will be prefaced by the script AS in front of it to stand for aspecular. So if we'll use an example, if your observation angle were -60 degrees and your illumination angle is 45 degrees, then the ASTM nomenclature would be 45 degrees colon -60 degrees. If you wanted to use the aspecular terminology, you could go 45 degrees colon AS -15 degrees for that same angle combination. And above you have a chart here to clarify the relationship between the illumination angle, observation angle, aspecular angle, and the standardized terminology. For simpler applications, typically those that only use absorption and metallic pigments, you may only require color measurement at 3 angles for good quality control. The 3 primary angles that are used for such applications are the face, the flash, and the flop. The face is the color of the surface that is observed in line of sight along the normal of the surface. That is, this is the angle at which the surface is facing the observer. The flash is an angle near the specular angle, but not quite the specular angle, and is usually aspecular 15 or specular negative 15 degrees. This would be near the highlight when you're viewing the surface of an automobile. And finally, the flop is the color observed at a large angle to the specular and is called the flop color. When the flop color is different from the flash color, the specimen flops. This is the color that you will notice when a sample contours away from the normal. Realize that more complicated applications, especially those involving interference and pearlescent pigments, may require additional viewing angles to fully characterize the product for successful quality control. Flop index essentially describes the lightness difference between the flash and flop angles, with the other terms in the function used to scale. Here, 15 degrees a specular is used as the flash angle, while 110 degrees a specular is used as the flop angle, and 45 degrees is the normal to the sample. Note that different organizations will use different angles for the flash and flop angles. Similar indices can also be made for hue angle and chroma. Lightness flop is typical of metallic paints, where the lightness changes much more with angle than do the hue and chroma. A flop index of 0 correlates to no change in the lightness with angle and a perception of solid color at all angles. And to think about this conceptually, the color would appear to be matte if there were no clear coat applied. A flop index of 10 correlates to a moderate flop between the lighter and darker appearance with illumination and observation angle. On the left here, we have a vehicle with a low flop index, while the car on the right has a higher flop index. And you can obviously see how much more the body is accentuated when you have a higher flop index. As mentioned, you can also have color flop. This typically occurs with pearlescent and interference pigment coatings and is characterized by a distinctive hue and or chroma shift with varying illumination and observation angle. But again, with interference and pearlescent coatings, you probably want to observe a little more than just the 3 primary angles. Here's an example of lightness flop. On the left is a specimen when viewed from the face angle, and next to it is the view at the flop angle. A circular standard is moved between the 2 angles to illustrate the 2 colors are indeed the same, but their appearance difference is the result of the viewing angle. Such large lightness flop is often used, as we've seen, to accentuate the contours of vehicles. Now let's examine the CMM6 patented double path technology. So far, we have only discussed 1 illumination angle and 6 observation or measurement angles. In reality, the instrument has 2 illumination angles and 12 observation angles. This allows 2 sets of measurements to be taken for the same sample. The sample is first illuminated from the left and measured at 6 aspecular angles relative to the specular angle that would be on the right. Then the sample is illuminated from the right and measured at the same 6 aspecular angles. Of course, this time it will be relative to the specular angle on the left. Then the measurements are combined into a single set of 6 aspecular measurements that compensate for curvature of the sample. Measurement time in the double path mode is longer than the single path mode, but it increases repeatability of measurements on curved surfaces. So, for flat surfaces, single path measurements are as reliable as double path measurements and can be used to reduce your measurement time. What this accomplishes? Well, The double path technology allows the instrument to be placed on curved surfaces down to a radius of 300 millimeters, which is about 30 centimeters or roughly a foot. And it also allows the instrument to have low sensitivity to who is actually operating the device, because the repeatability of the sample placement is improved. Also, this form factor does not require any pins to detect that the sample is aligned for reliable measurement, and this avoids the possibility of scratches from those pins and allows also for a smaller footprint. This smaller footprint in turn allows for single-hand operation. Other multi-angle instruments may require two hands to correctly position and operate. The CMM6 also has a small measurement area with a 12 millimeter diameter illumination area and a 6 millimeter diameter measurement area. This is great for measuring most small parts. However, a custom aperture is also available, which can more repeatedly measure very small parts such as the sonar sensors. The CMM6 has some other nice features that make it easy and comfortable to use. These include the small footprint and the lightweight design. It's a little less than 2.5 pounds. Also, the instrument has M6 by 1 thread per millimeter threads on both the top and on the side of the instrument. This makes mounting the instrument for a fixture or assembly line convenient. Konica Minolta also offers a Bluetooth module so you can be untethered from your computer during measurement while you're still collecting the samples to a SpectraMagic DX or Colibri file. The CMM6 also has a removable lithium-ion battery. You can purchase a secondary battery and charger so you can swap batteries out if you have long periods of measurement without any downtime to recharge. The screen on the CMM6 can also be inverted, which makes reading the screen much easier if you want to lay the samples on top of the instrument. So you can actually place the instrument upside down and it lays nice and flat, and you can place your samples on top. The standalone user interface has a variety of ways to view your data. This includes absolute colorimetric data such as L star, A star, B star, lightness, redness, greenness, yellowness, blueness. But you can also have colorimetric differences displayed, such as delta L star, delta A star, delta B star, and delta E 2000, among other metrics. You also have several different graphs that you're able to view, and you can use the arrow buttons to change between your view screens. The instrument has several other screens that aren't shown here, and like for example a simple pass-fail. And you can also turn the visibility of these screens on and off so that you display only the data that's of interest to you. So you can simplify your workflow by reducing the number of screens you have to navigate. Or you can make certain that you're able to see all the data that you're interested in at the time. Now we will look at how a CMM6 might be used for a quality control application. Here we have a target or a working standard made of a flat panel. Then we have sample 1, which is a flat panel that might be used to see how a sample compares to the working standard without introducing any new geometry differences. Samples 2 and 3 are two different curved surfaces, with sample 2 having a radius of 500 millimeters and sample 3 having a smaller radius of 300 millimeters. These might be representative of some other curved surfaces that would be on an automobile. And finally, we have a side view mirror that sample 4, and this is a real production part that would need to be analyzed on the assembly line. We can measure all these parts with the same instrument, the CMM6. And in an automobile, you might have the different geometries like these that need to be compared to a single standard. Because of the limited time we have, I've highlighted the 3 parts that we'll look at briefly, and those include the target, sample 3, which has a radius of 300 millimeters, and sample 4, which is the side view mirror. We have lots of data because we have spectral data for 6 different angles, and this data can be analyzed many different ways. Because I'm working with a pearlescent coating, I'm mostly interested in the color shift. So I'm looking at A star and B star components. You could alternatively use hue and chroma. Just depends on your preference. As you can see, sample 3 has a pretty close agreement with the target for both A star and B star. However, the side view mirror, sample 4, has large differences in A star for 45, 75, and 110 degrees, and even larger differences for B star at negative 10 and 15 degrees. Note all the angles I've mentioned are aspecular. Also, please note that the scales for A star for both samples are the same, and for B star, the scales are the same, but the scale for A star is different than the scale from B star. These data suggest that the appearance between the target and sample 3 are closer than between that of the target and sample 4. The color shift difference might indicate that the orientation of the effect pigments, or maybe some other morphology parameters, are not similar enough between the target and sample 4 for the part to be accepted. And please note that this is a very brief analysis just to give you an example, and there are many different parameters you could analyze, including spectral data. We have covered some examples of gonioapparent applications, and I've given a brief introduction to effect pigments and how they interact with light. This was followed by an overview of the geometry for multi-angle spectrophotometers. And we have shown that the CMM6 is designed primarily to easily measure gonioapparent effects with high repeatability. Konica Minolta is a global company, but we have representation in a location near you. Thank you for your time, and feel free to ask questions.
Thank you, Stephen. That was an informative presentation. We would like to start our question and answer session now. If you'd like to ask a question, please enter it into the chat box. Okay, we have our first question. What software works with the CMM6?
So we have a few different options for software for the CMM6. So the graphs that I showed you were from our quality control software, SpectroMagic DX. And that one will allow you to do a lot of different comparisons of a variety of measurements. And then we also have another software that can be used for quality control called Colibri, and it's a platform software which is great if you're looking for something that's more of an enterprise model. So like if you have multiple locations and you want to share data and you'd like to have a centralized database where you can store all your data, the Colibri platform would be a good solution for that, to manage your data across multiple locations. And then we also have available a software development kit. So that is, it is free of charge, providing that you sign a non-disclosure agreement, and that has to be approved by our headquarters in Japan. But what that will allow you to do is to directly interface with
the instrument, and you can then incorporate, you can pull all of the data, all the measurement data into your own custom application that you design in something like MATLAB or Python. You'll be able to interface with your own software. But keep in mind that we don't support your program, so it's and we don't support the SDK. It's just we will give you the protocols in order to interact with it and make your own custom software. But it's a nice tool to be able to use.
Okay, we have a lot of questions coming in now. Can this spectrophotometer be used for coatings with effect pigments over 100 UM?
Can this be used for coatings that have effect pigments over 100 micrometers?
Yeah.
So yes, it can. Just keep in mind, though, that if you need information about the structure, then you may need to have something else in order to tell you about any other features about the surface structure. So the M6 is still a useful instrument for those applications, and you may also need, when you're having these larger particle sizes, you may also need to worry about your orientation of the instrument. So if there's any rotational effects, you may need to define in your standard operating procedure how exactly you're going to account for any anisotropic structure. So if your grains are elongated in one direction, you'll need to specify what orientation you're going to measure at, or you may need to specify that you're going to measure at multiple orientations.
Okay, next question. The differences in A star and B star in sample 4 were due to different color pigments or due to different curvature of the sample?
That's a good question. Yeah. So yes, they are different curved surfaces, but from this data, I would think that it's actually not the curvature that's causing this color difference, because when we're measuring normal, and the instrument will, because I was using the double pass feature, it will compensate for that orientation. So this shift is actually it can be due to the orientation of the particles on the surface, or it could also be something where it could be something wrong with, maybe you have the sample maybe had a different size particle, but probably the most likely reason for this is, I didn't mention this, but this side view mirror is a different substrate. So the substrate that this is coated with is actually plastic, and here the substrate is metal, and the morphology will influence the color. So because this is a curved metal surface, and this is a plastic structure, it's most likely that the surface finish, the underlying surface finish below the coating, are actually different, and that will give an indication that this is probably the cause of these discrepancies. So a lot of times when you're having a different substrate, you may have a different a different range of acceptability for these more complex applications where you have different substrates using the same type of coating.
Okay, this question, what is the maximum curve that the CMM6 can work with?
Okay, so the maximum curve is infinity. The minimum curve is 300 millimeters, which is about 12 inches. And that correlates to angle of declination of 2 degrees.
Okay. Okay, when the display changes with orientation, is that automatic, or does the user need to do something?
I believe the user actually has to go into the menu to change that orientation.
Okay. Is there a Bluetooth or wireless way for the CMM6 to communicate with our computers?
Yes, so the instrument, let me go back. So it's not built in. So in order to keep the size compact, the Bluetooth module is actually an external piece. So on the strap, there's a strap to hold the instrument. You place your hand in here. You have the option of a Bluetooth module that plugs into this top port. So you'll see there are 3 ports on the instrument. One is for the power, one is for data. It uses a standard USB Type B cable, like an old printer cable. And then the top one is a mini USB to connect to the Bluetooth adapter.
Can the CMM6 be used to measure matte coatings?
Yeah, so the CMM6 can of course be used to measure matte coatings, but it's not going to be very useful if you know that the surface is going to be matte, because a matte coating means that the light is going to be scattered uniformly in all directions. So a matte coating is, you could almost see it's almost diffuse. And that's another terminology that's commonly used in optics. And because of that, that means if you have incident light coming into the sample, the light that is reflected from the surface will be uniform in all directions, or relatively uniform in all directions. So that means there's very little specular component, and that also means that you won't see much of a difference between the 6 different angles. So a lot of times if you're going to use a matte finish, you may want to use something like a regular spectrophotometer. But if you have applications that are doing both, where you have some that are matte finishes and some that are gonio apparent, so like ones that are using metallic effects or pearlescent effects, then you may want to use that to make sure you're doing QC, to make sure that your finish actually is matte. Or maybe you're making it nearly matte, but you want just a little bit of change. That's something where the CMM6 would be useful.
Okay, next question. The repeated measurements were done at the same spot or different spot. Were the repeated measurements done at the same spot or in different spots of the same sample?
In my methodology, I use different spots because I could have tried to use the same spot and then sample replacement, and that would get my results to be tighter, I would imagine. But for my operating procedure, I wanted to do an average because I'm doing these spray outs and I'm trying to make sure that I'm being representative of the whole part rather than just one area of the part. I do, however, on these spray outs, like on these 2 samples, I'm going to avoid the edges because similar to drawdowns, you have your flood zone. Well, also on a spray out, you're more, not necessarily, but you're more likely to have some defects near the edges. Yeah.
All right, we have the final question. We do have some other questions that are very specific applications, so we're going to reach out to those people individually in the coming days. But our final question for today, and this is a really good end question: what are good sources to learn more about effect pigments?
All right. Well, I've got a list of sources here right now, but the number one that I would look at for learning about effect pigments is this first one here, Industrial Color Physics by George A. Klein, and it's translated by Todd Mayrath. It's a very it covered a lot about effect pigments. Another good reference, though, is also at the spectrophotometry, accurate measurement of optical properties of materials. These are the editors. It's by a number of authors, but it covers a wide range of topics for color measurement. And these two are just good overall references for color. Yeah, but the one I'd recommend the most is Industrial Color Physics.
Okay, that takes us to the end. Again, thank you for attending. Stephen, thank you for a great presentation. An on-demand version of this webinar will be made available shortly, and we will send you a link for your viewing and to share with your colleagues. Again, thank you very much for attending, and have a good day.